Welcome back to a new video about Bessel response filter design. This is our example number 4. In this example we'll discuss the LC ladder configuration of the band stop filter design using this Bessel response filters. Of course we will work out this step by step in our calculations and also verify these in SPICE simulations. So let's look at our example. We have the following objective. We like to design a Bessel response passive LC ladder band stop filter. And it must have a 50 ohm double terminated shunt input circuit. Again, our generalized filter here, we have an R source and R load. They are normalized to 1 ohm, and there are specifications here also for our filter. The maximum passband ripple must be 1.5 dB. The minimum stop and attenuation is 55 dB. The lower passband frequency is 200 kHz. The upper passband frequency is 1 MHz. The lower stop band frequency is 400 kHz and the upper stop band frequency is 500 kHz. So let's see how we can design these circuits, the filter using these specifications. The solution, the first step is our passband normalization coefficient, as we did also in the previous videos for our Bessel response. So you need to find this CP, the coefficient. So for a given maximum passband ripple, in this case 1.5, we can relate that to the passband normalization coefficient CP. And that lies between 0 and 1, so there is a number between 0 and 1 which relates that A max between 0 dB and approximately 3.01 dB. So there is a table that will list then this value of this coefficient using this A max value. And this table is shown here, which will then also give us the filter. Not exactly, but we can then pinpoint this later more carefully. But looking at this 1.5 dB, you can see that the coefficient, the passband normalization coefficient, must be then 0.7168. But we see that it must be a second order up to 10th order, still not really clear. So how can we make this more exact? We need to use also this stop band attenuation information. So we can say for a max of 1.5 dB, we already know that the passband normalization coefficient CP is the 0.71680. And this number is important. We will use this in the next steps. So the passband bandwidth and also the center frequency for our band stop filter. The bandwidth here is the difference between the upper and the lower passband frequency. So it's also 2 pi times the difference here, which is 1 MHz minus the 200 kHz. So they give us, of course, here 800 kHz. So that's actually also in radians per second here given. 1.6 pi times 10 to the power 6 radians per second. The center frequency is again the geometric mean between upper and the lower passband frequency. Again, also written in this format. So you can calculate now the given values. Here will be then 2.81 mega radians per second or million radians per second, or 447.2 kHz approximately. Step 3 is now the normalized passband frequency and also the normalized stop band frequency of this prototype low pass filter. Again, remember, we always start with the design of a low pass filter and then transform that to a band stop filter or maybe a band pass filter or a high pass filter. So the base is always the low pass filter design. So for that we need to first determine the normalized passband frequency. That is then given by this formula. You substitute the values here, it's always 1. The next one is the normalized stop band frequency, omega s, which is then in a similar format than omega bandwidth divided by the upper minus the lower stop band frequency. And that's in this case, given the information here, will be 8. So now the transition sharpness, omega r, capital letter omega r, will be then the omega s over omega p, which is 8 over 1, will be then just 8. Next step, step 5, is the calculation of the normalized transition sharpness, because now we have a transition sharpness, but now we make it normalized, and therefore we will use now the CP we determined in step 1. So omega r from step 4 and also CP from step 1, we multiply them together, you get now 5.7344, and this number is now important in the next steps. Now, before we move on with the next step, let's also calculate this scaling factor, band stop frequency scaling factor, which is KFBS, which is given by this expression, the bandwidth times this scaling factor, the coefficient from step 1. Now we know it is 1.6 pi times 10 to the power 6 from step 2 times the 0.71680. Now when you do the calculation, you get here 3.603 megaradians per second. Now one of the important steps, step 7, is the filter order from this graph. We know that this graph is very important. This is our normalized transition sharpness from 1 to 10. And this, in the vertical axis, we have now stop and iteration going from 0 to 140. You see here lines that will then also determine your order. So first order, second order, third order, fourth order, etc. So we have lines here. How do we determine now, carefully, our order? Because we said it must be between 2 and 10. So 2 and 10, so second or 10th order. Exactly, we don't know yet. So for that we need this graph. So we just first draw this 5.7344, this line, and there's also a line for 55 dB for attenuation, and there is an intersection here which is exactly, almost exactly at this line, which is our 5th order. Let me zoom in a little bit so you can see more carefully where the intersection is. Again, this normalized transition value, and this sharpness, and this is also the passband attenuation we need, and this is now the intersection. So we need the 5th order here, almost exactly 5th order. If it was, for example, below this line here for the 5th order, still we need to have a 5th order because it was at least 5th order, so above 4th order. So we need to have integer orders. So let's go back and then continue with the normal presentation. So we require NS5 for this sharpness, normalized transition sharpness. Continuing with our next step, step 8, for the low pass to band stop filter transformation. This is the low pass 5th order circuit. You see the C1, L2, C3, L4, C5. So we see here now the 5 components. Again, RS and RL are normalized to 1 ohm each. Now we need to make a transformation. Now before we move on with the transformation, let's also use this table from the Bessel response, normalized element values. And since we need a 5th order, the element values are shown here. So x1 up to x5, you see here the coefficients. And each of them is actually the value of the capacitor here and also the inductor there. So the capacitor C1 will have a normalized value of 0.1743 farads. And this x2 is actually related to that L2, which has a value of 0.5072 henries. And C3 will then have 0.8040 farads, etc. So then L4 will be the 1.1110 henries, and then also the final one for C5, this value. But they are of course normalized, so we need to use these values to get the practical values for our design. Now what does this low pass to band stop transformation means? We make actually the capacitors a series capacitor and inductors, as shown here, and each inductor will be replaced by an inductor and a capacitor in parallel. So we have now this circuit transformed to this circuit. You see actually this is a series combination, this is a series combination, and this series combination. You see that here, here, and here, and this will be a parallel combination shown here. And this is also parallel combination shown here. Now the component values for this filter will be then calculated like this. So we have the CS1. You see again the frequency scaling factor, the C1 from the table. So it's actually shown here, and also the Km, the magnitude scaling factor, and also the omega center, which is also shown here. Now when you do that calculation, you get now 1.591 nanofarads. In a similar form, you do it for the LS1, which is this inductor, and also for the CP1 and the LP1, which is for this part. And the CS2 and LS2 is similar to the first row, and the CP2 and LP2 is similar to the second row. Again, looking at the L4, which is actually this coefficient, and also L4 here. And for the CS3 and the LS3, we use the coefficient here, which is the X5, which is then calculated like this. So we see that we use the omega center, the band stop scaling factor, and also the Km in these calculations. And for RS prime, which is the scaled version from the normalized RS, which is just 50 times 1, which is 50 ohm, and also for the load, it's the same 50 ohm. So we have now the complete set of these values for our design. Okay, now taking all these component values together, we see here we have now 10 reactive components, so 5 capacitors, 5 inductors, and we have 2 resistors. And now the complete design is actually complete. Now we can also say what's the design circuit. Now this is the design circuit in the simulator. You see here the prototype low pass filter, which is our 5th order Bessel response prototype low pass filter. And here we have our design circuit with these component values. You see that also 1.591 nanofarads here. You see also this LS1, which is 79.62 micro henries. Also the other ones is all shown here. Okay, now let's also verify this in the simulation results. This is the body plot of the gain. You see the body plot. And you see here several things like the passband gain, which is minus 6.02 dB approximately. Why? Because at the passband, for example, at very low frequencies, this filter will behave as an unity, so it will then behave as a gain of 1, and then we have attenuation of 50 over 50 plus 50 because they are scaled up. That will be then 50 over 100 will be a gain of 0.5, and 20 log of 0.5 is this minus 6.02 dB. And similar for very high frequencies, you get now these 2 labels. The next one is the gain at this 200 kHz, which is our lower passband frequency. You cannot see it here. Now it has a value of this one, but with the base value was this, so going down from minus 6.02 dB to minus 7.5 approximately, is going down approximately by 1.5 dB, a little bit less. So the maximum passband ripple is now achieved because it is now lower than this 1.5 dB maximum allowed. And now for the other one, the upper one, you see actually a similar value, but it is hair larger, so 1.5006 dB at 1 MHz. So we can say this is the problem. For most practical purposes, this is perfectly fine. Of course, we want to have a little bit less, but this is perfectly fine for this case, also for practical purposes. Now for the lower stop band attenuation, you look at 400 kHz because that was actually our lower stop band frequency. You see this value is minus 61.21 approximately dB. Again, going down from the baseline, we go down by 55.19 dB approximately, which is at least 55, so that's also according to specifications. And upper stop band frequency is also shown here, again going from the baseline down by 55.24 dB approximately, again at 500 kHz, again according to the specifications. And this center frequency is also very close to what we have calculated. So you can see actually all of the component values and also the specifications are met, except this one, which is a hair larger than this maximum allowed of 1.5 dB. Alright guys, this is our example number 4 about this Bessel response using the LC ladder filter configuration for our Bandstop filter. If you have any questions, comments about this example, please let me know. I will try to answer them as soon as possible. Help us to reach more people for these interesting topics and videos, so like and share these videos so that we can reach more people. Thanks for your cooperation and see you next time in another video.